Okay. The reason why the second semester is so tough is because this means so much. Okay? Now, let's just start, and you may use your calculator to do this. Like, start by, and actually get the answer to this 2 different ways. And I'd like you to do it in the graphing mode as one way, and then tell your neighbors how you get the same answer as your calculator without using your calculator. So I love my calculator because it does a very good job visualizing what's very important today. Okay? In the graphing mode, when you do second calc 7, and you say from 0 to 2, that visualization is really important. I think it's really important. Don't graph an integral. You can evaluate an integral on a home screen, but don't graph an integral. Graph a function and have your calculator get the integral. If you try to graph an integral, what happens? Like, if you tried to just graph this, I think it takes a long time to do it. Don't do that. It's doing the accumulation every single time. And if you use different x values, it would change, like, and it's going to take forever. So you don't do that. You should say, hey, graph x squared and get the accumulation of it from 0 to 2. All right, we get this 2.667. How do we get that same answer without a calculator? Very important. We could take the antiderivative. Plug in 0 and 2, the c is not going to matter. You get 8/3. Okay? What your calculator shows a beautiful picture of is the visualization of how it gets the answer, how it accumulates, how it gets that area. This integral in this form means area. What your calculator does to get that answer is it accumulates. How it does that, we'll find out by the end of class. What you do to get this integral, what you did to get this answer, 2.667, is you took an antiderivative. Okay? Today, we are going to focus on the idea that this accumulation means area. Okay? And we are going to try to evaluate this integral, but I'm going to say you don't have a calculator. You don't have a calculator. So, Pirelli, just flip it over. Just flip it over. Don't look at it anymore, okay? So, you would try to take the antiderivative, but I don't know what the antiderivative is. So I don't know what this antiderivative is. I don't have my calculator, so I can't accumulate. I don't know what the antiderivative is. So what this equals to, I have no idea right now. Okay? Here, this guy. Okay. Area. Well, I'm not given an equation, so my calculator can't accumulate. I could take the antiderivative, but when I do, I get big F, and that doesn't really help me. So like, yes, I can, but no, it doesn't help me. So I still want to find the area, but I can't do either of these two things. All I'm given is a limited amount of information. I'm given some points. Okay? I don't even know how these points are connected. Cool? So what we are going to do is not get what this is equal to, but we are going to spend today approximating that. We are going to spend today not figuring out what this is equal to, but instead figuring out what it's approximately equal to. How can we approximate areas? So for example, this is G, this is from 0, 1, 2, 3, 4, 5. Like, I want you to approximate the integral from 0 to 5 of G. The question is how? You guys can do it. Like, give me an approximation for the integral from 0 to 5 of G. Give me a number and tell me where that number came from. Where'd you get that? So you are getting the number 8 from where? So if you understand that this means area, well, you can use your friend geometry. And you can use your friend shape. Because we know how to find area of shapes. Rectangles, triangles, right? And this is a 2 by 4, this is 8. This is a 2 by -2. So this is like -4, where you kind of understand underneath the x-axis would be like a negative displacement, negative accumulation. And this is a 1 by 1, this is 1. So you would think of this integral as meaning area. And you can use geometry to approximate area. You can add up all these shapes, and you get 5. That's today. That's what we're going to be doing. But the question you might be thinking is like, well, like, what shapes? What if I use like straight lines here, and I wanted to use like triangles and rectangles, you know? And maybe I feel like this is a semicircle, so maybe I'm going to use the formula for a semicircle of a radius 0.5, you know? Like, wouldn't that, like, how do I know what shape to use? How do I know how many shapes to use? Like, what if I wanted to use like a bunch of different rectangles and a bunch of different triangles? Well, there's a guy who I thought of this. His name was Bernard Riemann. And Bernard Riemann says, you know what? Let's formalize the process so that you don't have to think about what shape to use when and how many shapes. I'm going to tell you what shape to use. I'm going to tell you how many shapes to use. You just do what I tell you to do. Got it? And he created a Riemann sum. So the Riemann sum will like tell you what shape to use, tell you how many shapes to use, and tell you how to use them and how to create them. So it's like a formulaic way to use shape to approximate areas, where areas are approximating integral, accumulation, antiderivative even, whatever that is. Got it? Okay. There are 4 types of Riemann sums. So 4 different like situations Riemann created. He came up with a left, a right, a midpoint, and a trapezoid. The left, right, and the midpoint all use rectangles. Rectangles all have the same area formula, width times height. Okay? But depending on the type, you'll use specific widths and heights. The widths will be the same. And the last one is a trapezoid. Uses trapezoid. Well, that's easy. We'll talk about the formula for the area of a trapezoid later. Okay? We are going to start with the approximation of our second scenario, where I'm just given a table of information. Okay? Cool. And Riemann's going to tell you, hey, approximate this integral using 4 subintervals indicated with widths indicated by the data. How about that? With widths indicated by the data. All right. And again, the left Riemann sum is going to use rectangle. Area of a rectangle, height times the width. The width will be an x distance, a change in an x. It's either going to be indicated by the data or you'll be able to calculate it. We'll talk about how you're going to calculate for a different example. Here we're doing indicated by the data. What's that mean? Okay. Using 4 subintervals tells me like the amount of objects. Okay. I want to use 4 objects with widths indicated by the data. Means I'm going to say, okay, the first object's width will be from 0 to 2. The second object's width will be from 2 to 3. The third object's width will be from 3 to 7. And the last object's width is from 7 to 9. Okay? From 0 to 2, this is the width of my first rectangle. It's 2. I'm going to put that number there. That's very helpful to have down. The width. From 2 to 3, that width is 1. So put that one down. From 3 to 7, that width is 4. Let's throw that one down. And from 7 to 9, the width is 2. All right, so we have the width of all of the rectangles. Now we just need the height. The height is going to be determined by the y value at the leftmost point of the interval. Or more simply, the y on the left. So left Riemann sum, that means we're using height of y's on the left. Okay, what does that look like? Well, visually on the graph, I'm using this y coordinate on the leftmost point of this base. I will use that height for that entire base. Or from 0 to 2, the base 2, height of 1. And then we just calculate the area, right? This is geometry. We're approximating area, right? This integral stands for area, and it's area because of what's after it, but we'll talk about that later. So we got a height of 1, a width of 2. I get 2, so I'm just going to throw that 2 right there. The next one from 2 to 3, I'm going to use the height of 3, which is on the left of the interval. Height 3, width 1, that's the 3. From 3 to 7, I'm going to use the height. Over the leftmost point, that height is -2. -2 is what I'm going to use. Height times width, -8. This is -8. And then from 7 to 9, I'm going to use 5. With 2, height 5, that's 10. 10. Okay? So what's my answer? Yeah, you just add all these up, like this plus this plus this plus this. 7. This is my approximation for my area. Is this going to be accurate? I have no clue. Don't say no. You have no idea. You have no idea how you connect these points. You don't know that you're connecting them like this. You don't know that. Maybe I connect them like this. Maybe this is a phenomenal approximation. You know what I mean. You don't know. The key is Riemann doesn't care. This is what you get when you use this method. You got it? Don't care about accuracy. We'll talk pretty quickly, pretty soon, about like how we can get more accurate of an answer. Okay, but for right now, it's just like, that's what we get. All right, let's see if you understand. If we are asked to find a right Riemann sum, again, using 4 subintervals with widths indicated by the data, right Riemann sum uses rectangles. I bet you could figure it out. Areas are heights times width. The widths will always be these delta x's, these change in these x's, these x distances. But now the height are the y on the right. All right, see if you can do it. And then you get 32. Yeah, good. Zero to 2 with 2 is the height of 3. 0 to 2 using 3. Height times width, 6. Two to 3 with 1 using a height -2. Height -2 with 1, that's -2. Just get the answer. Get 32. All right. 3, 2, 7. You won't even need the picture in the future. Using the height of 5. Height times width, point. 7 to 9 with 2, height 4. Eight. Add them all together. This is approximately 32. Using a right Riemann sum with 4 subintervals, widths indicated by the data. Is it accurate? I don't know. I don't care. That's what I get. Cool? All right. Next one's a midpoint. Rectangles, again. Height times width, again. Width, delta x, again. Height, y in the middle. Now, I would not ask you to find a midpoint Riemann sum for this data because I'm not given the information that I need. If we were to consider the first rectangle from 0 to 2, you don't know what the y value is in the middle. You might think, well, isn't it 2? You don't know that. It could be 5. It could be -7. Right? Cool? So like, you don't know that. Don't assume it's 2. So I would not ask you to find a midpoint Riemann sum for this one. So let's do another example where I would ask you to find a midpoint Riemann sum, and we'll see how, this is the last page of your notes, this whole delta x calculation can start to come into play. The last page before the next lesson. Second to last page before the last lesson. I'll go back one. There it is. Okay. You got the MRS, stands for midpoint Riemann sum. MRS, midpoint Riemann sum. We want to find a midpoint Riemann sum to approximate this integral from 0 to 6 using 3 subintervals of equal width. Cool. So it's like, what is the width of all of my rectangles if I want 3? 2. How'd you figure that out? Yeah, there's like an interval from 0 to 6. I want only 3, so I kind of divided it. Now what you did intuitively is this calculation. B minus A is like the overall basis distance divided by n, which is the number of objects. And you intuitively did 6 minus 0 over 3 to get 2. The delta x is 2. Do you have a question? You go. Okay? Now, you're starting at 0, you're going to 6. You have to have 0, you have to have 6 down. But you would go from 0 to 2. That would be object number 1. What is the base length? 2. What is the height you're going to use? The y value over the middle, which you have. Okay? You don't calculate it, it's given to you. Okay, keep going. Cool, we get 6. That's the midpoint Riemann sum, what it's equal to, but that's the approximation of this integral. All right, let's see if you really know what you're doing. Please find a left Riemann sum using 6 subintervals with equal width. Six subintervals, left Riemann sum. That means the whole 0 to 2, 2 to 4, 4 to 6, that's only giving me 3 objects. I need 6 objects. 0 to 1, the 2, etc. And you get, after all that, 7. What's really cool is you notice, since you're multiplying by 1, since the base of the rectangles are all 1, you don't have to worry about like multiplying by 1. You just add up your left height. It's like a 1 by 1 plus 2 by 1 plus negative 1 by 1. Like you don't need all the 1. So you just need the 3, the 4, the negative 2. You leave out the 0. It's not used. And that's okay. You get 7. Great. One plus 2 minus 1 plus 3 plus 4 minus 2. 7. All right. One more, trapezoid. Uh-oh. No more rectangle, trapezoid. I didn't even tell you what the area of a trapezoid is. Anybody remember what the area formula of a trapezoid is? You? How do you find it?
Like you do the top height times the top height minus the height right there. I know how to do it in theory. It's just like.
Well, here it is. Does anybody remember the formula? Two triangles and a rectangle, sure. But what's like an easy formula instead of having to calculate all those triangles and the rectangle? Nope. Man, I should call your geometry teachers. Be like, yo, they don't remember the formula for this area of a trapezoid. I don't know. Could you do it efficiently? I don't know. It is 1/2. It is 1/2 the height times the sum of your bases. That's what you said? Did anybody get that? Yeah? All right. That's an easy formula so that you don't have to do that many calculations, which you guys are all like talking about. Sure, we can find the area of a trapezoid. You actually have been finding areas of trapezoid. Because our trapezoid, I'm going to show you the first one, and then we'll go into the formula for our specific situation. Our trapezoid, still going to use this width, this delta x. It's going to use both of the heights. And our trapezoid looks like a triangle on top of a rectangle. It's a trapezoid. And I'm just going to draw the picture for the explanation of this one. So rotate it. So. Cool. All right. This part is the delta x. This part is our first height of the height on the left. This part is the height on the right. Take these things, fill it into this formula. Go! Take these things, fill it into that formula. Take those things, fill it in the formula. Yeah, but I want like the generic formula, right? A equals 1/2 delta x times y left plus y right. Cool? This is what we're going to use. For our first trapezoid, 1/2, width of 2, heights of 1 and 3, 4. On your test, you had these. You could have used this formula instead of splitting it into a rectangle and a triangle. You probably still will split it into a rectangle and a triangle, but you could use this formula. For example, like, let's look at 7 to 9. Write down your width, using both of your heights. There's your trapezoid. Nine. Now, the ones in between are not fun to draw / visualize. You could connect these points with a straight line, and it ends up being two triangles, but like you don't know what the base length is because you'd have to calculate it using this. So, you know what we do? You know what we do? No, you just don't worry about it. You just use the formula. Okay? You just use the formula. You don't worry about the visualization. This is 1 times a half. That's a half. This is 6. I don't have the shapes drawn though because it's confusing. Now, guys, heads up, real quick. On your homework video, I don't put these numbers down. This is like new. I don't think I'm going to update the homework video, but I find this is very important. It's like having the width written down, pointing to the height you're using, whether it's one or both, and then doing your calculations. I find people who mess up on what ends up being not that bad, right? Like, what do you think about this so far? Not that bad. Not that bad, I hope. Okay? It's not that bad. But since it's not that bad, like, don't mess up on it. Okay? Now, what's bad and what's like, why is this tough, is that we have to remember everything from the previous 2 units. Okay? But you will be asked not to find the exact, I'm just making this up, so don't start looking around. I'm not going to ask you to tell me what the exact value for this is. But I might say, approximate this using a left Riemann sub with 3 subintervals indicated by the data. No. No. It's easy. Like, you'll get the answer. But then I might ask you, explain that. What's it mean? Nope. Nope. This is where everybody fails. Like, let's get the value. Ready? Let's get the value. We got a 2 by 5. We got a 1 by -2. And we got a 1 by 1. So we got a 10, a -2, and a 1. So 10, 11, 10, 9. Oh, my goodness. What a beautiful number. And then I take that, which is this, I multiply by 1/9. I say that this value is approximately 1. Great, you got a point. What's that mean? Average what? What? So everybody who says average and then says something other than velocity, you're wrong. If you said average rate of change, if you said average position, if you said average distance, if you said average displacement, you're all wrong. This is an average V. You got to remember 1 over B minus A. Integral from A to B of something. What is it? The average something. So it's not that the calculation of the number is tough. which is the new stuff, it's like you have to remember everything from the last 2 units. Let's say you calculated something like this. You got an answer. How would you interpret this? What's the meaning of that? It's not an average change. It's just the change in F. It's the displacement of F. What is this? What is this? No, it's the change in X. It's the displacement of position. What did Newton teach you? Nothing, apparently, but what Newton should have taught you is that you use an antiderivative. And what we really first did, and like it does not take that long for you guys to forget this, is that your calculator calculates this by accumulating the velocity. You calculate this by finding a change in position, which is why this means displacement. This means displacement of F. This is F of 3 minus F of 0. It's that you guys all screw up on. So we are like still kind of reviewing, but we're just like calculating the value by getting an approximation. All right, prove me wrong. What if I ask you to approximate this? Distance. Yeah, you don't remember that. You don't remember that. No. What if I ask you to calculate this? Wrong. The average position. The average position. Speed is the absolute value of velocity. When you accumulate speeds, you get distances.
Oh, so you just take away the 8.
So guys, when you're doing your homework, the calculation of the Riemann sum, sure, that's half credit. And yeah, you need to practice that. But like, this is why this unit is so tough. This stuff, like, you got to remember its meaning. Why is this unit so tough? It's like, oh, all you have to do is put a fraction in front of it and it's an average. But then everybody forgets what it's the average of. The average of position. Oh, this is accumulation of speeds. That's distance. Oh, none of you knew that this was just a change in F. It's a displacement of F. This is a displacement. This is a position. An area under a derivative. An area under a rate. Change in the total. Okay? You can't forget that stuff. You don't understand what stuff means and like what's the point in calculating it. All right? All right, well, let's say this was F prime. What would I get if I found this value? A change in F. Very good, guys. We're getting there. Okay. So I'm going to get some sort of number, but I'm going to get an approximation. And what that means is it's a change in F. It's a displacement of F. Great. Good start. Now, I don't have a calculator, so I can't plug this in. So the whole accumulation that my calculator shows me, I can't do. I can't take the antiderivative. So that doesn't help me. I still want to approximate the area. Great. What does that area tell me? The change in F. Great. What should I do?
Do a Riemann sum.
Okay. With what?
We'll plug in values from 0 to 3.
Yeah.
And then we'll
make a table. Make a table. Make a table. Plug in points. Make a table.
Are we doing
now,
numbers?
you're going to make a table based on the following thing that's going to be told to you. I would like a right Riemann sum using, how many would you like to do?
2.
3 is a good idea. 4 is a horrible idea. 6 is doable, but I'd prefer not to. But you picked 3, which is a wise choice. Equal width. Because if you're going from 0 to 3, and you're using 3, what's your width? 1. Now you need to include 0, your starting point. You need to include 3, your ending point. But if you have a width of 1, there's a couple homework problems when your width is not 1, and it's not a nice number, so you got to pay attention. You're going to go from 0 to 1. There's 1. 1 to 2. There's 2. 2 to 3. There's 3. Okay, great. That's the x values. That's going to give you your width. But we need y values. What are y values? Function values. Taking your x, plugging it into your function. Well, actually, you know what? This is f prime. My bad. This is f prime. I said that was f prime. Taking your x's, plugging them in to whatever you have, getting the y values. Then using the Riemann sum. Plugging in 0, I get 0. Plugging in 1, I get 2 over 2. 1. Plugging in 2, I get 4 over 5. Plugging in 3, I get 6 over 10. 3 over 5. Okay, please give me the right Riemann sum using 3 subintervals of equal width. The answer is 12/5. What does it mean? It's an approximation for the change in f. For this example. F. One times 1 plus 1 times 4/5 plus 1 times 3/5. 12/5 is my approximation. What does it mean? Change in f. Great. Now, through another analysis, we will be able to determine if that is an over or under approximation. Wheeler. Remember approximations from earlier in this course? What other kind of approximation have we done, Wheeler? No. Yeah, we used a equation of a line. A specific line was a tangent line, and we used a tangent line to approximate y value. We'd use a tangent line, we would then get a y value and a tangent line to approximate a y value on a curve, right? And what was important about this? Understanding if it was over or under. This is over based on the curvature of the function. We always want to know if approximations, whether or not are accurate, not super important, but at least if we know it's bigger than what I should get or it's smaller than what I should get, that's a lot of good information. So we are going to do the same thing with these approximations. This is our second and last approximations that we have to know. If you go and study the BC calculus material, there are other approximations we get to, and we have to talk about over and under with that stuff too. So, for tangent lines, it's all about curvature. Concave down, over approximations using tangent lines. Concave up, under approximations. Let's see, is it going to be the same way here? Will curvature make Riemann sums over or under? Well, we got to start with a Riemann sum we want to look at, like a left Riemann sum. Let's look at a left Riemann sum. Now, it's easy to do, like, visualize a left Riemann sum over an interval. Just like draw a rectangle. Okay, I'm going to use the y value on the left. This is my y value that I use. Boom. Here is my left Riemann sum's area, whatever that is. Is that over or under the area under this graph? It's going to be under, right? Obviously, it's under. It is less area than all this area underneath the graph. Now, would that change based on concavity? Okay, tell me why. Which one is it different for? Because with tangent lines, it changed with concavity. But it does not change with this Riemann sum. Why? Because left Riemann sum uses the y's on the left, and if your function is increasing, the y's on the left has got to be the smallest values, right? Well, what about a right Riemann sum? If your function is increasing, regardless of the concavity, the y-coordinate on the right has got to be the biggest one. So it's going to be an over approximation. What about a trapezoid? Tell your neighbors, what about trapezoid? Morelli, hit me. I'm open. You're exactly right. There's no concavity. It's right on it. If it's concave up, it's more. If it's concave down, it's less. You're going to have to be able to visualize the graph, and then based on the type of Riemann sum you use, understand if it's over or under. Left and right Riemann sums will always be like this if your function is increasing. That's your explanation. You might be asked to justify why is it over or under. You would say left Riemann sum's an under because my function's increasing. You don't have to go anything further than that. Function's increasing, you don't even mention concavity because the concavity does not matter. All right, well, what if the function's decreasing? Switch. Positive y's, negative derivative is a left Riemann sum over or under. Figure it out. Explain why. Now your explanation, you guys want to write a lot, you want to do a bunch, but like from A to B or 0 to 1, if you're using the left Riemann sum, you're using the largest value. It's over y, f is decreasing. That's all you have to say. F is decreasing, a left Riemann sum for a decreasing function is going to be over. Just say that. We don't care about concavity. It's not even given to us. Now, let's go back 1 second. You don't have to flip, but I'm going to go back. What if I wanted a better number than 12/5? What if I'm like, you know what, I don't think that's going to be accurate. I want it to be more accurate using a right Riemann sum. So I'm going to stick to right Riemann sum, but I want it to be more accurate. What should I do? Yeah, use 6 instead of 3. Because if I use more rectangles, or more trapezoids or more things, you know, like I'll be given more information, I'll be using more information about the function, I would get a more accurate answer. So this is very important. It's not about the accuracy of each individual Riemann sum. It's not about lefts being better than rights or trapezoids being better than this or midpoints being better than this. It's the fact that for any of them, more objects, better approximation. For example, 0 to 3 using 3 shapes. Not going to be as good as 0 to 3 using 6 shapes. Now what's happening to my objects as I'm increasing the amount of them? Let's go 12 shapes. The object's widths are getting smaller. 0 to 3, 3 shapes, 3 minus 0 over 3, the width is 1. 0 to 3, 6 shapes, 3 minus 0 over 6, the width is a half. 0 minus 3, 12 shapes, 3 minus 0 over 12, a quarter. Cool? More shapes, more subintervals, delta x decreases. Okay? Now, how many objects would you use before you felt like really comfortable about like, hey, that's probably like really close to the exact amount? As many as possible. Infinite is the right idea. And what would that look like if you put an infinite amount of rectangles? It would look like a bunch of skinny lines good rally. It was fun. It looks like a bunch of lines that be added up. Okay? Right? Wouldn't that look like that? All right. So what we've been doing, and here's the chicken egg situation of calculus. I do the egg before the chicken. Most teachers do the chicken before the egg. What we've been doing is we've been taking a sum. This is a sigma. This is a capital S in Greek. Stand for sum, right? You've seen sums before. And we've been summing areas of rectangles for right Riemann sum. I mean, we summed trapezoids too. Okay. Well, we've been summing up height times width, right? Okay. Where did the height come from? Where did the width come from? Where did the height and width come from for all of our examples? The width is the change in x. What was the height? The y outputs, and the outputs came from plugging in an x into a function. Cool? And we did n objects. And to make it like a little bit more specific, we want to tell them like what x's did you plug in? Well, like you started from the first x and then you went to the nth x. Okay, cool. And how do we find delta x? Well, if they were equal widths, it was b minus a over n. All right. Better and better approximations, more and more rectangles, right? How many rectangles do we want? As many as we can, or an infinite amount of rectangles. Okay, mathematicians are like, man, this whole idea of finding areas under curves that are not geometric, like areas under functions rather than areas under like semicircles, so like things that we don't have equations for, this is the idea behind it. Let's try to approach infinity with the amount of rectangles we're using. Let's do an infinite sum. We don't like to plug in infinity, we like to approach it. Hey, look, Mr. Limit's back. Calculus is all about infinities and infinitesimals. Okay? They were so excited about this idea of an infinite sum that they're like, you know what? We're going to use this a lot. And they're like, let's, instead of having to write down this limit and this summation, which takes a while, let's just like do a shortcut. Let's use a tall, skinny f. And that stands for infinite sum. Yep. And what are we doing? Height times width. What are the heights? They come from a function. What are the widths? It's a delta x. But you know what? You guys just told me that the objects become really skinny, right? So if we're talking about b minus a over n and n's going to infinity, we're talking about something approaching 0. So it's not really like a change in x, it's like an infinitesimal, an instantaneous change in x. We've been using this in the past to represent an instantaneous change in x. For example, dy dx is tangent slope because it's instant change in y over instant change in x. The width is an instant change in x. To designate where we start and where we end, this whole b minus a business, we'll put it right here. So, you know that your calculator accumulates. The idea behind this accumulation is that your calculator does a Riemann sum type process to approximate an infinite sum. The reason why this is area is because you're doing an infinite sum of heights times width. That's why this is area. All integrals aren't all areas. For example, you BC calculers, they were infinite summing, and you guys infinite summed this. You got distance. BC Calc students infinite summed this. And it gave us distances. You can infinite sum, and actually the application of the integral is more used to understand that we're taking an infinite sum. We are accumulating this stuff. In Unit 10, we will find volume by using an infinite sum of something else. And it was our friend Newton who then discovered the connection between infinite sums and antiderivatives. Newton discovered the connection that this integral also means antiderived. Take the antiderivative. What is this? The change in big F. Maybe it's better to use F prime and say it's the change in F. This is Newton's discovery. Now, most AB Calc students do the Riemann sum, infinite sum approach first. And then they go into Newton. I kind of like taught you the Newton stuff first. And now we're going back to realize that it's just an infinite sum. Okay? So, accumulate, infinite sum, antiderivative. It is an area because it's an infinite sum of height times width. We will find that stuff inside integrals aren't always f of x dx. Depending on what you want to accumulate, you can accumulate other things. If you take, say, you're a biology major, and you take Calc 1 for biology sciences, even though you shouldn't because, like, it's going to be a piece of cake. you will be accumulating using like a program different rates. And it's the idea of these infinite sums of those things that can tell you things about what's going on in the world. Okay? So the integral actually starts with an infinite sum. It's Newton who discovered the connection with infinite sums and areas. Now it's important for the lesson to like remember that. So let's go to the last page of the lesson. So let's look at this guy over here, 0 to 6 of h prime. Now you look over to the right, and you see a table of information. And you're like, all right, what kind of Riemann sum should I be using? It's all about rectangles, right? This is important. Why this is also tricky is because you got to understand, like, what this means. Well, what does that mean? It's a change in h, right? Well, I can find the change in h. Boom, that's the exact answer. I don't need to approximate. So we got to keep the Newton idea of like antiderivatives might be able to give you the exact answer. Now you look at this one, and you should always think, oh, can I take the antiderivative? Yes, I can, but does it help me? No, it does not. And this is when I would have to approximate. In your homework, I do a very good job of leaving things that you got to do a Riemann sum for, and then like throwing them out, and all of a sudden you have to do a Riemann sum. The reason why the second semester is so complicated is because this means so much. It means antiderivative, it means accumulation, which is really just an infinite sum. What your calculator does is actually a very complex type of Riemann sum to accumulate. It does a sum of height times width. It sums up a bunch of skinny rectangles. Your calculator does that. What you do is you take an antiderivative. Because of all of that, there's so many meanings. And keep track of the meanings while you're doing your homework. Yeah. I am done.